Okay, so this is going to be our problem solving session for our chapter 7 worksheet. And this one's going to be looking at periodicity and atomic structure. And so for this one, what we're going to be looking at is kind of how we can convert our wavelengths into energies and frequencies. Now, the thing to remember is that when we're working with our wavelength, there's kind of two equations. One is that our energy is equal to Planck's constant times v, the frequency, and that the speed of light is related to our wavelength and our frequency. So when it asks us an infrared wave is measured to have a wavelength of 5.6 times 10 to the 4 nanometers, what is its frequency? What we're looking for is this one. Now we know the speed of light, that's 2.998 times 10 to the 8 meters per second. And frequency is 1 over a second. That's how often we see that wavelength in 1 second. So for us to convert that over, we know that our frequency v is going to be the speed of light divided by our wavelength. So we need to divide it by our wavelength. So that's 5.6 times 10 to the 4 nanometers. But before we use that number, we have to first convert our nanometers into meters. So where our units cancel. So 1 meter is 10 to the 9 nanometers. So our frequency should be 2.998 times 10 to the 8 divided by 5.6 times 10 to the 4. And make sure that's in the parentheses. So that way we're dividing both by the 5.6 and the 10 to the 4. And then we need to multiply that whole thing by 10 to the 9. And so our frequency becomes 5.35 times 10 to the 12 frequency. So that's 1 over seconds. And if we look at our significant figures, then we should have 2. So that becomes 5.4 times 10 to the 12. Okay. Our next one, it says almost all commercially available microwave ovens employ radiation with a frequency of 2.45 times 10 to the 9 per second. So they would like to calculate the wavelength of this radiation. So this time, we're still using that same equation, but instead of solving for frequency, we want to solve for wavelength. So our wavelength should be the speed of light divided by the frequency. So our speed of light is still 2.998 times 10 to the 8 meters over 1 second. Our frequency is 2.45 times 10 to the 9, and the seconds should go on top because it's per second. And so we need to take that 2.998 times 10 to the 8, divide that by 2.45 times 10 to the 9, and we get 0.122. And that's a 223, but we have 3 sigfigs, so just 0.122. And then that should be meters because our seconds will cancel. And so wavelength can be in any type of length. So it can be in meters, it can be in nanometers, whatever we're using. Right, so you just want to read through the problem. If it doesn't say, then you can choose any unit that you want as long as it matches. Let's look at this next one. So an FM radio station broadcasts at a frequency of 9.87 times 10 to the 7 per second, or 98.7 megahertz. And we want to calculate the wavelength of that radio wave. So from there, it then asks us what is the energy of 1 photon of this radiation, and then it gives us Planck's constants afterwards. This is also on your equation sheet. So if you don't have it listed for that problem, you want to use your equation sheet. So calculate the wavelength. And so we still use that same equation. We have 2.998 times 10 to the 8 meters over 1 second. Our frequency, 9.87 times 10 to the 7 seconds. And so that's going to give us 3.04 meters. So when you're listening to the radio, that wavelength is actually a whopping 3.04 meters long. Right? So almost 3 meters, or almost 9 feet before you see that wave repeat again. So they're really quite long waves. From there, we want to figure out our energy. And to figure out our energy, then we're going to use this top equation. Our energy is Planck's constant times our frequency. So we're going to take our 6.626 times 10 to the negative 34 joule seconds. And we're going to multiply that by 9.87 times 10 to the 7. And then this per second is on the bottom. And so our seconds cancel. And so we're going to get that just in our joules. So 6.626 times 10 to the negative 34 multiplied by 9.87 times 10 to the 7. And we get 6.54 times 10 to the negative 26 joules. That's what we're looking for. So we have our wavelength and we have our energy. And so each time as you're working your way through this worksheet, what you're really trying to do is just make sure that you're using the correct equation, that you're setting up your units correctly, and then you're converting them. So let's look at this next one. Light with a wavelength of 400 nanometers strikes the surface of metallic cesium in a photocell. And the energy of the electrons ejected from the metal is 4.97 times 10 to the negative 19 joules. Verify Planck's constant using that information. So what we want to do is we want to have our light here, or sorry, our light's coming in with a wavelength of 400 nanometers. And so it's causing this energy to get ejected. And so what we want to try to figure out is how much energy there is from our wavelength versus the electrons that are being kicked out. So what this is doing is we're basically assuming that the energy of our light is equal to that energy of those electrons that are getting kicked out. So the first part is we know that our energy is related to Planck's constant times that velocity. And so they want us to verify Planck's constant. So we're looking for that H, not velocity, frequency. Sorry, bad habit. And so what we want to try to do is we need to convert our wavelength into our frequency. So 400 nanometers, its frequency is going to be C over our wavelength is going to give us our frequency. And so 2.998 times 10 to the 8 meters over second, 400 nanometers. 1 meter is 10 to the 9 nanometers. Nope, sorry. Got those flipped. We need them going the opposite way. So we need 10 to the 9 nanometers up on top, 1 meter at the bottom. And so that frequency becomes 7.50 times 10 to the negative 14. Not negative 14, just 14 seconds minus 1. And then we can plug that in for our frequency and use that energy. So we know that the energy is 4.97 times 10 to the minus 19 joules. We can divide that by its frequency, 7.50 times 10 to the 14. And that's going to give us 6.631 times 10 to the negative 34 joule seconds, which lines right on up with our 6.626 times 10 to the minus 34 joule seconds as well. And so just like that, we've managed to verify Planck's constant. Now it also asks us what is the color of the light used on that metal. And so in order for us to do that, we have to first pull up our range of our visible spectrum with its wavelength. So here's our chart with our visible range in there. And so 400 nanometers would give us, so our 400 nanometers would give us light that's right there in that violet range. Very good. Now let's look at the next one. Both blue and green light eject electrons from the surface of potassium. In which case will the ejected electrons have higher average kinetic energy? Then we need to explain it. So let's think about this. If both of them eject electrons, so they both have enough energy to break our electrons free. The one that's going to eject faster electrons is going to be the one that has more energy. And so that means that when those electrons are excited, they're given more energy to them, so they're going to go faster. They're going to have more kinetic energy inside of them. So we're trying to figure out which one has more energy, our blue or our green. So our energy is related to the frequency. And so the higher the frequency goes up, the higher our energy. Now our frequency is related to our wavelength, but they're inversely related, right? So our frequency is going to be C over our lambda. That means that as our wavelength goes up, our frequency actually goes down. And if our frequency goes down, then our energy goes down. So that's telling us that the wavelength is inversely related to our energy. The higher our wavelength, the less energy we have. So our energy is inversely related to wavelength. So our wavelength with our light with the longer wavelength will have our lowest energy. And so between blue and green, blue has a lower wavelength than green. So blue is a shorter wavelength. And therefore has more energy than green light. So the electrons ejected will also have more energy. Okay. You could also solve for them and find the energy at the blue, which is about 400, and green, which is about 550, and you could plug those in there as well. What is the speed of an electron that has a de Broglie wavelength of 100.0 nanometers, knowing that the mass of an electron is 9.11 times 10 to the negative 31 kilograms? So what we want to do with this is we need to add in another part. And that's that our energy is not just related to our HNRV, and that's because now there's a mass associated with it. So some of our energy gets changed when we talk about the velocity because we have a mass now. Now we're shooting out electrons as opposed to photons, which don't have mass. So our equation is really looking at our wavelength is Planck's constants times m and v this time, where v is our velocity. So if we want to find the velocity, then we need to put that up by itself. This part stays the same, and then we need to bring our wavelength over. So our velocity is going to be Planck's constant, 6.626 times 10 to the minus 34 jouleseconds. Our mass is going to be 9.11 times 10 to the minus 31 kilograms. And our wavelength is going to be the 100.0 nanometers. But we want to go ahead and convert that over into our meters. And so we want to times this by 10 to the 9 nanometers over 1 meter. Oh, made a mistake. We want those nanometers to cancel, so I should have the 1 meter on top, 10 to the 9 nanometers at the bottom. Now, the reason why we're using the kilogram and we're using meters is we want to remember that a joule is related to our kilograms and our meters for its units. So 1 joule is kilogram meter squared over seconds minus 2. So if we multiply joule seconds, that's really kilogram meter squared seconds minus 2. We're going to cancel out one of them because of the times by the seconds. This whole thing is getting divided by a kilogram and a meter. So that cancels out another meter, that cancels out the kilograms. And so we're going to be left over in meters per second, which is a velocity. And so that's why we want to use those units the way that we're using them. So once we plug it into this equation up here, that's going to give us our answer, which is 7.2, oh, sorry, wrong box there. 7.27 times 10 to the 3 meters seconds. Let's look at number 7. 7 is asking us something very similar. We still have our wavelength is equal to our h over our mass times its velocity. And so it asks us, what is this, or find the wavelength in nanometers of an electron of mass 9.11 times 10 to the negative 31 kilograms moving at 3.00 times 10 to the 7. So now we just need to plug that in. We have our Planck's constant. We have our mass. We have our velocity. So it's just plug and chug. And that's going to become 2.42 times 10 to the negative 11 meters. And they want us to get that into nanometers. So we need to multiply this by 10 to the 9 nanometers to 1 meter. And so we get 2.42 times 10 to the minus 2 nanometers. Okay. Let's look at part 8. Find the wavelength in nanometers of a baseball of mass 0.41 kilograms moving at 85 miles per hour. Oh, so that is a lot. So we got to do quite a bit of conversions there in order for us to move that along. Because remember that at the end of the day, we're still going to plug into this equation, h over mv. So before we find our wavelength, that's going to be in meters. And so for us to use our velocity, we have to go from mph to meters per second. So let's look at this. We have 85 miles per hour. Now for our hour, let's go ahead and change that first. I think that one's the easiest. If we want to get hours to seconds, that means 1 hour is 3,600 seconds. You can also do that as 1 hour is 60 minutes, 60 minutes, or 1 minute is 60 seconds. So that's good. That's going to cross off our hours. We're in the seconds. Now we got to do our next part. We have to get miles to meters. So what we can do is we know how many feet there are in a mile. And so there's 5,280 feet in 1 mile. We also know that there's 12 inches inside of 1 foot. And 2.54 centimeters is 1 inch. And now we should be able to go from centimeters to meters. So there is going to be 100 centimeters instead of 1 meter. Whew. Quite a lot there. So 85 divided by 3600 times 5,280 times 12 times 2.54 divided by 100. And at the end of that huge chain, we get 38 meters per second. Now we just need to plug that back in. So 6.626 times 10 to the minus 34 joule seconds, 0.14 kilograms, 38 meters per second. And we're going to find our nanometers. Oh, so that becomes 1.3 times 10 to the negative 34 meters. We're going to convert that into our nanometers. (1.3 times 10 to the 25 nanometers). And now you can see why when you throw a ball, it doesn't seem to act like a wave. It doesn't seem to fluctuate much because its wavelength is so very, very small. We can't see it. And that's because of how fast it's moving and also the size, it's kilograms. All right. So looking at 9. Yeah. So 9 is having us look at the difference between an absorption spectra and an emission spectra. So for this next one, we're trying to look into our emission spectras and our absorption spectras. And so we can get this actually from a book. We don't have to go to Norton because we already have a book that has it. This was for a different class where we were trying to do open source. And so when we're looking at this, what we want to talk about is the difference between absorption and emission. So absorption spectra are obtained when the elements in the element absorb the energy from a source. So that means that if this was our element over here, the light is being shined on that. And we're looking for that spectra of what they've absorbed. The emission spectra, on the other hand, is different. This is when you have the element, we've excited it, and now that element is going to release photons at different wavelengths and energies to produce that spectra. So one of them is related to those electrons being excited from one energy level to the next, and the other one is what happens after we've excited them as they fall down. So absorption spectra and emission spectras are a little bit different. So elements exhibit line spectra instead of continuous emission spectras, and that's because our energy levels for our element, they exist in very specific bands. So we can't have electrons inside of that element at all values. It's what we call quantized energy levels. It's what's preventing our electrons from just all colliding into the nucleus and decaying over time. And so those bands that get emitted is because those electrons can only make certain transitions. And each time it makes that transition, it releases a wavelength or a photon with that energy. And so only specific wavelengths can get released. When we talk about orbitals, we're really talking about energy or electron shells, but it's an area that has a high probability of finding an electron. We know that those electrons are traveling around inside of that atom. And based on all of the repulsions, this is the area that we think there should be a high probability that they're going to be at. But we don't know for sure whether they're there because of Heisenberg's uncertainty principle. But we know that 95% of the time, it should be somewhere inside of that orbital. And so that's what we're describing. Now there's three words here: the shell, subshell, and an orbital. Now your shell, you can kind of imagine it's similar to your energy level. It's basically that row on the periodic table. So that would be the 1, the 2, the 3. That's what energy level our electrons are going to be associated in. The subshell is going to be the smaller region inside of that. So that's going to be kind of like their orientation. Or not orientation, sorry. That's going to be like their shape. And so those are the letters, S, P, D, and F. So it's the shape that that electron orbital takes on. And then the orbital is actually the region and orientation that we have that high probability of finding that electron at. So as an example, so a shell of 1 is telling us that we have an energy level of 1. The S is telling us that it's going to be a sphere, which is its subshell. And the orbital is going to be which of those regions it's in, which in this case for the S is only one region. If we did P as our subshell, then we could have one that's aligned along the x-axis, we could have one aligned along the y-axis, or we could have one aligned around the z-axis, and that would be our orbital. Now, the further that we move away from the nucleus, the probability decreases. We're most likely to find our electrons near the nucleus because there is that attraction between the electrons and the nucleus. The farther we move away from it, then the less likely we are to find those electrons out there, because now we're getting to that outer edge of that orbital, and then eventually that electron is going to be lost from that atom because there's no more attraction between that electron, or such a small attraction between that electron and the nucleus that it could be lost. Now, there is electron-electron repulsion that gets involved in that process, and so we do see shielding that happens from other electrons. But the general idea is that the farther away from the nucleus we get, then the probability of us finding electrons begins to decrease and decrease. Now, they're asking us to draw the S, the P, and the D orbitals. And so our S1 should be a sphere. And there's only one orientation of it. Our P1s are kind of the dumbbell shapes, so they're the two balloon ones. And there's 3 orientations. They can be lined up either with each of those axes, right? So we can have it going along the X, the Y, or the Z. Or sorry, I actually have these flipped. This is normally the X, and that's normally the Z. And the D ones, now they have the 4 lobe setup. So they can be along all of those planes. So they can be along this plane here. They can be along the next plane. So that's between them. And then they can also have our rings. So instead of me drawing them, I think I'm just going to show you the picture of our d orbital. And so this is an example of the d orbital shapes, right? You can see how they kind of take, moving that around. They take orientation along those planes, kind of filling in those gaps. And so where there's 4 of them, 1 for each of the planes, and then the last one is kind of this dumbbell with this ring around the middle, with the donut. So that's our d orbital shapes. So now we have to fill in the maximum number of electrons that can exist in each of those orbitals. So the maximum number that exists in any orbital is 2. There's always a spin up and a spin down. That's the most that we can fit. How many electrons can exist in the p orbital? Well, we have 3 orbitals there, and each one can fit 2. So that's a total of 6 electrons. How many electrons can exist in 2px? Well, that's a specific orientation. So that orbital can only contain 2. inside the n equals 2 shell, so that's that energy level. How many p orbitals are there? Well, each energy level has 3 p orbitals because they have the 3 different orientations. Our d subshell fits 10 electrons, and that's because there are 5 different orientations. Each one fits 2. How many subshells are allowed in the n equals 3 shell? Well, for our d, that's going to give us a total of n equals 3. So we can have our s, our p, and our d. And so that gives us 3 different types of subshells. How many d orbitals are there? Well, each energy level can hold 5 orientations of our d orbitals. So there's going to be 5 of them. And so inside that n equals 3, we have 2 in the s. We have 6 electrons in the p. And we have 10 electrons in the d. And so we can fit a total of 18 electrons in the n equals 3 level. Now, looking at these principles, right? So the Fabry principle is electrons are placed in orbitals of increasing energy. That means that when we fill in our electrons, we need to start from the bottom and work our way on up. So an example of that would be that lithium, it starts off with 2 electrons in 1s2, and then it moves up into 2s1 as it fills that in. The Polyexclusion principle is this idea that our electrons can't have the same 4 quantum numbers. So what that means is that inside of an orbital, so let's say that this is the 1s, we're going to have 1 electron that spins up, and we're going to have 1 that spins down. So this is like hydrogen to helium. Those 2 electrons can't have all 4 of identical quantum numbers. So that spin up one, it would have an energy of 1, an orientation of 0. Its orbital would also be 0. And so one of them will be plus 1/2. And then the other one will be 1, 0, 0. And the other one will be minus 1/2. So it's spin up and spin down. Hundjoule is the idea that each electron will fill an empty orbital first before they start doubling up. And so if we look at n's p orbitals, so this is the 2p, has 3 options. Now, instead of partnering them up and looking like this, what we really have is 3 half-filled orbitals moving into it. And so that's what we're looking for. And then this last part is go ahead and write our electron configurations for the following atoms. And so we're going to use the longhand for this one, and then we're going to use the shorthand on the next ones. So we need a periodic table, and then we should start putting those in. So calcium has a total of 20 electrons. So we start at the bottom, 1s2, 2s2, 2p6. So that's accounted for 10 of those electrons. 3s2, 3p6. And remember that we don't go into the 3d orbitals first. We need to go into the 4s, so this should become 4s2. And that's all 20 of our electrons. Chlorine is going to be in that next row, and that's going to be 1s2, 2s2, 2p6, 3s2, 3p6. No, not p6, 3p, and then only 5 of them in there for this 17 electrons. Gallium, 31 electrons. So we have 1s2, 2s2, 2p6, 3s2, 3p6. Then we're jumping down into the 4, so 4s2. And now we have to do all of those transition metals. Now remember that the transition metals go back up. So that's 3d, 10 of them. And then we're back to 4p1 for gallium. And titanium is a total of 22 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. And so that's how we can kind of move from one into the other. Our electron configurations. So when we're doing the shorthand, then our shorthand means that we can use those noble gas simplifications. So let's look at bromine. Now bromine has 35 electrons. And so the noble gas right before it is argon, argon with only 18. So from argon, we need to add in that 4s2, 3d10, 4p5. For chromium, we can go ahead and start that one off with argon as well because it's also 24 electrons, 4s2, and then 3d4. Now this one is an irregular one. So it's really going to be argon 4s1, 3d5. But we'll talk about our irregular notations up in the up and coming lectures. If you're watching this after the first lecture, you actually could just stop right here when we're getting into our emission spectras. You don't have to move into all of that orbital stuff yet. We're going to continue to clarify that in our second lecture for chapter 7. But if you have done it, then you can keep on going. Oxygen is going to end up being helium, 2s2, 2p4. Gold, or silver, not gold, is going to be krypton, 5s1, 4d10, so another irregular one. If you didn't know about the irregular ones, then you might think it's 5s2, 4d9. Our copper is just like silver, except it's one above it. And so our copper is going to be argon, and then 4s1, 3d10, right? Because it is also an irregular one. Rubidium is going to be krypton with the 5s1, and then molybdenum is going to be a krypton 5s1, 4d5. So you can kind of see that these last ones, we're really trying to get you to practice your irregular ones. And so that's going to be covered in the lecture, but remember that there's basically only a few of those that we have to memorize. And unfortunately, there's not really a great way to know them all. We have to just memorize them. Orbital diagrams, what they're looking for is just the valence electrons, so the ones in the highest energy level. And so what we want to do is we want to draw out our orbitals as lines or boxes, and then we are going to fill them in. So for chromium is 4s1, 3d5, so it's got valence electrons past that noble gas core. So that's going to be our 4s and our 3d. Now, because it's 4s1, we should get 1 in there, and 3d5, and because of 100, then we should have those all separated out, 5. Oxygen, on the other hand, now oxygen is 2s2, 2p4, so we should have our 2s and our 2p. And remember, p has 3 orbitals, s has 1. So you can either do the boxes or the lines. I generally prefer the boxes. I find that nicer, but it's up to you. And so for our 2s, we should have 2 electrons in there, 2p4, 1, 2, 3, 4. So just one of them should be doubled up. Silver is going to be our 5s1, 4d10. So that's going to be our s. That's going to be our 4d. And so we should have 1 in our 5s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's actually all filled inside of the D. And the last question, why do elements with the same electron configurations exhibit similar chemical properties, like how they react? And that's because when they have the same electron configuration, they tend to gain or lose the number of electrons in the similar way because they have the same number of valence electrons. And so because they gain and lose similar amounts of electrons in similar ways, then they generally go through the same types of reactions. So they're not going to be identical, but they're going to be similar. All right, I hope this was helpful.